Hello, I'm Stacy Ross, and this is my presentation for Lab 2, Lines of Charge. The purpose of this lab is to create a more sophisticated model of the electric force of charged tapes. In Lab 1, the purpose of the lab was to observe the amount of excess charge on an ordinary object with respect to Coulomb's law and the concept of superposition. Coulomb's law states that electric force is equal to the constant K multiplied by charge 1 and 2 and divided by the magnitude of R squared. In Lab 1, I prepared pieces of charged tape by placing one piece of tape on a flat surface, then another piece on top of it, which is referred to as the upper tape or U-tape. I carefully removed the U-tape from the bottom piece and observed its interactions with neutrally charged objects. Finally, I observed how two pieces of U-tape interacted with each other. This lab is much like Lab 1, except instead of treating the tapes as a point charge, we want to model the charges as being evenly distributed. From the experiment, I was able to observe that the U-tape was attracted to both my hand and the table, but it was repelled by the other pieces of U-tape. From this, we can conclude that the U-tapes have the same charge. To determine what charge the tape had, I held the U-tape to a pin, which I knew to have a negative charge. If the U-tape had a positive charge, it would be attracted to the pin. If the U-tape were neutral, it would be attracted to the pin. However, the U-tape was repelled by the pin, so we can conclude that the U-tape is negatively charged, meaning there are excess electrons. The following calculations were performed under the assumption that charge A is equal to charge B. We can make this assumption because the tape was charged using the same method in the same environment. We are also assuming that we can ignore air resistance and that the charge is evenly distributed. We can find the mass of the tape given the dimensions of the tape and the average mass of tapes per meter. Using the gravity constant and mass of the tape, we can find the magnitude of the force of gravity on the floating tape. Given that there is a zero net force in the y direction, we can assume that the magnitude of the electric force in the tape is equal in magnitude to the force of gravity. Using the previous measurements and calculations, I created a computational model in GlowScript. This code is based off the source code provided in Lab 2 instructions. I started by inserting the constants, and then the equations, and finally visualizations and printed outputs. In Lab 1, we approximated the charge by solving Coulomb's law. However, in this lab, we are taking a different approach. Assuming that our charge from Lab 1 is correct, we can use a nested for loop in GlowScript to iterate over infinitesimal charges to find net electric force. We can then compare the magnitude of the electric force and the force of gravity. Because the net force is zero, the two magnitudes should be equal. We can then use the guess and check method to adjust the charge Q to make the magnitudes equal. I inputted the number of arrows I wanted to represent the evenly distributed charges as N. I chose n equals 25, which produced the following model with printed statements regarding the calculations I previously discussed. I found the adjusted Q to be negative 2.3255 times 10 to the negative 8th coulombs. Using this charge, the magnitude of electric force and gravity are equal. Again, we are assuming that charge A is equal to charge B, we can ignore air resistance, and that the charge is evenly distributed. If I had modeled each of the tapes as a single point charge, as I did previously, I could expect a smaller value for the charge Q. When treated as a point charge, Q was negative 8.66 times 10 to the negative 9th coulombs, while the line charge model gave a Q value of negative 2.3255 times 10 to the negative 8th coulombs. The reason these estimates differ so much is because the line charge takes into account the distance between each evenly distributed charge across the tape, rather than just considering the distance between the middle of both pieces of tape. For this reason, a higher number of arrows increases the accuracy of our estimation. The line charge model produces more realistic values because it considers the whole length of tape as a charged object rather than assuming the tape can be treated as a point charge in the center. That's all. Thanks for watching.